Good morning. Uh, we are in the day 6 of this GAN course on combustion theory and applications. Till this point of time, we covered up to the laminar premixed flame. Now we are going to look into the other category of flame, that is laminar diffusion flame. Now where we encounter this kind of flames, because when there is not premixed air fuel charge. So normally what happens in some cases, we get a kind of a laminar premixed flame, but once it interacts with the surrounding air, the flame also takes oxygen from the outside ambient. In such cases, uh, the it generates a different kind of flame that is called as laminar diffusion flame, because the fuel jet tries to diffuse the outside ambient air environment and try to generate this. Next thing, where we get such kind of situations that we have this laminar diffusion flame is, you can recall that when you look at combustion in the compression ignition engines, we spray a fuel jet through an fuel injector into air which is already at elevated pressure and temperature in the cylinder. So in that case, the fuel droplet is in fuel droplet try to mix with the outside air or air inside the cylinder and try to diffuse into it. Through this diffusion process, we have different category of flame, and this diffusion process leads to many number of flames, because the fuel is auto ignited, and since there could be n number of flames which can be generated at various locations of the engine cylinder depending on the equivalence ratio. So under this heading, we will try to analyze some of the topics like laminar jet. Normally, when these diffusion flames are formed when you spray fuel jet into air. So a typical situation would be that combustion of fuel jet in an auto ignition of fuel jet when it sees the air. But to simplify that analysis, we are looking at a situation what we call as a non-reacting laminar jet, because when the combustion happens, we cannot see the main fuel and air, rather we see the combustion product. But to simulate them in analytically, we can do this with an ideal gas analysis, assuming the fact that fuel and air are mixed and they provide a jet which is typically which we call as non-reacting. But the end results or trends that we get out of it, we can extrapolate it in a combustion environment. But we don't have luxury to have analytical equations when combustion is happened, and using that combustion product we cannot frame this analytical equation. That's the reason we make these assumptions to be non-reacting laminar jet. We are doing same thing, but at this combustion product side we are assuming that the fuel and air, they remain as it is and they don't create the products. Products means we are basically looking at the mole fraction which remains at the reactant side and product side to be same in this air fuel mixture. Then by doing this, we can frame this mathematical description for the jet flame, and this mathematical description of jet flame gives the understanding the laminar flame structure. Here I mean that when the jet comes out, it talks about what is its initial momentum, how fast, how long it can go, what is the jet characteristics, how far it can spread, all sorts of information that we can get. So we call them as a laminar flame structure. Then we'll in my previous discussions, I emphasized the word conserved scalar, and since it is a diffusion flame, and we are saying that there would be the equivalence ratio of fuel and air could be can vary drastically or from with different values, but what identity of fuel remains same, of carbon or hydrogen, that part within that jet flame, can you quantify? That's conserved scalar. So this is nothing but we are looking at the term called as mixture fraction F. Then these studies will help us to understand these heterogeneous combustions that commonly happens in a compression ignition engines. So in your earlier discussion of IC engine, we only emphasize that how combustion happens, but in these things and what happens and what are the different kind of structures that we are going to achieve, but how that shape is supposed to achieve, that we can get through this description, that is laminar jet flame mathematical description. So what is, I mentioned earlier some of the important parts of this non-reacting laminar jet. Now when you say non-reacting laminar jet, normally the classical device that can give you the range of flames is the Bunsen burner. By controlling the air fuel charge here, we can regulate the air fuel mixture, and the first type of flame which you get, this inner cone, which is a pre-mixed flame. Now if you do not give sufficient charge, only fuel, then this fuel can come out and it can diffuse with outer air, atmosphere, and then it can create an outer cone, and that is not through this, rather diffusion of fuel into the outside air, and we get this outer cone, that is a diffusion flame. Now how it can come as a jet? Now when it can come as a jet, because if you give sufficient momentum to this charge, so it can come as a jet, and this what you see, this particular structure, it will not remain as it is, it can travel much fast to a longer distance. We have a jet which goes, that is normally it happens in the IC engines. Now here the typical study for this kind of things, you see here in this combustion chamber where we have fuel injector, and when it is when the fuel is sprayed into this combustion domain, it comes as a jet, and when it comes as a jet, it tries to spread, and once one point is we have, and this is first set of flame. Second set of flame that can happen as a consequence of the first set. So that is what the phenomena of auto ignition is all about. So those kind of events we are trying to simulate. So initially it is a static flame which is we get in the Bunsen burner. Now when you have a jet, that we can say what you get in the fuel injector for a CI engines. Now what we are simulating here is a similar kind of phenomena, that fuel comes as a jet with some diameter of 2r, and it tries to mix with the outside air. But one assumption is that when it mixes, it's just a fuel air mixture, and when it comes with certain initial momentum, which is at location x is equal to 0. Now when it comes as a jet, it covers an axial distance x, and depending on the strength of the jet, its effect will be felt at some location. And since it is coming at a free coming to the air freely, there is no physical boundary just after this location. So what we say, it's a these two jets are the two limits which we call as free boundary, and which means that effect of jet is limited within that boundary. Now when it comes out, if you look at each plane, we have two possibilities, that and the flow is axial along this the central axis, and there is a radial variation which is r, and there is an axial variation which is x. So the starting point both the cases is x is equal to 0, which is just at the nozzle exit, fuel nozzle exit, and this initial cone, which is the inner cone, that happens to be distance xc, which is the initial cone. After that, it tried to spread with the outer air. So this is the inner cone xc, and what we are going to see here is this. So basically there are two parameters needs to be evaluated. First is velocity of the jet, because since it is a jet, if you look at pure fluid mechanics point of view, as if it's not a mixture, then it's like a water jet, or we can say air jet. So it's a only fluid mechanic point of view, we can say that we can find out the velocity at different x, also with different r. That means radial variation and axial variation, and that can be normalized with respect to its initial strength. The initial strength of that jet is limited by the velocity at x is equal to 0. So what we are going to plot is initial velocity is Be, and we are looking at a parameter, this ratio at any x r is equal to 0. We are looking at x at r is equal to 0. So, and this is what fluid mechanics point of view. Additionally, in this case, it is not a free air, it's a air fuel mixture. So that's what we have, this mole fraction YF or mass fraction YF. So if you try to plot it, so initially it starts with a with its own strength value 1, and once it goes after this initial core, it tries to decay. So this plot talks about how, what is the at different x, what is the value of V x0 by Ve or and Yf. So this is the domain which we are looking at. This one, what we are seeing is we are looking at each x1, what is this radial variations. So we are at each x1, we are looking at what is this radial variation. So this plot talks about it, and this is another x2. Another x2 means far downstream of this. So mole fraction which was initial at x is equal to x1, it further down, and this is the location at r max, which talks about this maximum value at this location. So then next step is that now what is the fundamental behind this? What we have is that we have a potential core. Second, we have the presence of viscous shear. Third, effect of diffusion. Okay, so in the potential core these defects are not felt, and which is somewhere in the initial domain. But when it comes out, particularly in the inner core, when it comes out to the, when it moves towards the outer core, all these effects comes into picture, and we are going to analyze that, analyze as if it's a nozzle fluid uh, uh, interaction in terms of mass fraction and the velocity fraction. So those analysis we are going to carry out, that at any x or any r, how do you make your judgment, what is the, what should be trend of the profile. So most important the thing is that there is an initial jet momentum which is conserved throughout the flow field, and the jet, as the jet penetrates with the surrounding air, the jet momentum is transferred to the air. So thereby the velocity decreases, and the greater quantity of air that are entered into the jet are carried away by the downstream. So when you look at this typical nature of the profile, this profile appears to be in the decay. It's called as a decay of the decay in terms of velocity and mass fraction of the fuel, and that is decay is both in radial direction and axial directions. And we see that at central line we have this maximum effect, and in the once you move away from this central line, its effect will come down. So the beyond this potential core, radial velocity decays from maximum to 0, which is from central line to the edge of the jet. Central line is this, and edge of the jet is this. Suppose you look at this particular plane, we have the central line point and the edge of the jet. So that is what these notations are there. Now we all know the Fick's law. Through this Fick's law concept, we can quantify the concentration of the fuel when it spreads through this diffusion term. Now next point, important point, is the effect of moving downstream into the downstream is to increase the time available for diffusion to take place. So it means that when you go downstream, means jet has enough time to mix with the surrounding air, because it has a wide range of domain of air entrapment, and so the width of the region containing the fuel molecules grows with axial distance, and central line fuel velocity concentration decays in a similar fashion as that of velocity. So basically effect of fuel and air concentration, they follow a similar pattern. So these are some kind of standard mathematical treatment. How do you go about it? So basically this is a case where it's a radial coordinates environment or cylindrical coordinate environment, r and x. So terminology that I mentioned here, that initial point which is at x is equal to 0, and at this point it is center point which is r is equal to 0. So that is the starting point, and at r is equal to 0 line we have this x plane which is x is equal to 0. First, potential core stands with a distance or standoff distance which is xc, and this xc talks about the peak point of this initial conical potential core. And when the jet spreads, there is a partition. So partition means we call this as a jet edge, which means that these are the imaginary partition, because there is no physical partition. These are the imaginary partitions that separates completely atmospheric air outside and the fuel air mixtures. So basically in this domain what you see, that air fuel mixture of various strengths. Some zones will have a high equivalence ratio which is towards center line. Some zones will have less equivalence ratio when you go towards the edge, and that happens at any x as well as any r. So this is the terminology that we use in terms of jet edge. So what we are trying to find out is that what should be the if you solve this kind of fundamental problem in a cylindrical coordinates, what we are trying to look at the concentration of velocity and concentration of fuel at various r and various x. So we are finding out a general fundamental correlations that can cater both. So the solutions for this problem lies in taking care the mass conservation equation in a cylindrical coordinates r and x. Then we have this axial momentum conservation because the effect of jet is only in the axial directions, that is momentum equation. Now in fluid mechanics term, these two equations are sufficient to quantify velocity, but in combustion viewpoint, since you are looking at fuel species, so you have to find out the species conservation equations in terms of its mass fraction. So here there is a term called as d, which is known as the diffusion coefficients, and this d, effect of d, we can say that how we can find this d through Fick's law, and these are the governing equations, and we are trying to solve with certain boundary conditions. First case is along the central line of the jet, which is r is equal to 0. So at that case we have the velocity rx, vrx, and for this the Vr and Vx, V is radial velocity, Vr stands as the radial velocity, Vx stands as axial velocity at different x. So these notations tells you that what velocity we are looking at. So at that location your dv by dvx by dr is equal to 0. Again similarly we can find for fuel fraction also. At large radius means if you go far away, at large radius fluid is stagnant where no fuel is present. So this is the condition of Vx, and this is the condition of mass fraction of the fuel. Another study we can another things as a boundary condition you can say at what is happening at x is equal to 0, means in this plane x is equal to 0 we can have r is less than or equal to 0, r is greater than 0, greater than r, small r is less than or equal to r is nothing but the diameter of the fuel nozzle, and that r can also be greater than 0. So this value stands as 0, but at any value it all depends what is the fuel mass fraction at that location. So with these boundary conditions, these are the main equations, governing equations. Second set, these are the boundary conditions, and another point is that we can calculate the momentum the flow of the jet at any x by considering its density, velocity along x directions and r. So if you find out that value terms as rho e ve square into pi r square. So that is nothing but your initial momentum, which is at x is equal to 0. Rho e and ve stands as the velocity at the exit of this nozzle. Rho e is the density of the at the exit. Density means fuel air chairs combined density. And fuel mass, this is the momentum. Also you need to find out the fuel mass. So same term is here, but with an additional term y fe. I think there will be square here because this is mass, fuel mass, and this term is momentum. So it's a mass term and this is a momentum term. Okay, so The solution lies in the fact that it has to be solved in a particular fashion which is similar to a similarity through similarity parameters. Those concept of similarity parameter was introduced when you talk about the solution of flat plate theory through Blasius equations. So there we introduce a term called as similarity parameters. Here also we are going to introduce a similarity parameters, because those complicated problems involving R and X and then finding combining all of them, because we need to analyze fuel and air fuel parameters in terms of its mass fraction. Additionally, we are also finding the velocity term. So both the things has to be combined in a single loop, and those things we are going to look at how they vary along R as well as X. So similarity index zeta is found for its solution, that is zeta. So it is this zeta takes its initial condition which involves this jet momentum at this initial stage Je. Rho e is the density at the exit of jet which of the air fuel charge, and this and also it is taken about the viscosity part mu. All these terms combined in a particular manner with a ratio R by X. R stands as radial direction and X stands as axial directions. So this is a very unique parameter which depends the initial condition of the jet, fuel jet, which is just at the exit of the nozzle, and this. So one interesting part is that this similarity parameter is it's a common term which can be used for calculating the velocity term as well as the velocity decay as well as the full mass fraction decay. Now through this process, how the equations, all those governing equations, when it is solved, it turns out to be a fashion which is called as non-dimensional axial velocity distribution, which is Vx by Ve, and where this is expressed in terms of Reynolds number, in terms of the ratio of X by R. Again there is a term zeta, this similarity parameter which drops in here. So entire terms here are non-dimensional. This is ratio. So this say that how the velocity decay takes place with respect to its initial velocity just at the exit of the jet with a function of X and R simultaneously. That means if you are fixing X and trying to find R, so that is with respect to X, Vx by Vx, and R is the fixed number, which is the twice R is the diameter of that jet, fuel jet. Now through these things we can find out similar term which is fuel mass fraction. Interestingly, this ratio and this ratio bears same value because it's a ratio. Now coming back to central line velocity, at central line velocity we have to find at R is equal to 0. So when you put that, we get out of this number, and we have this central line mass fraction as well. So along the central line this value remains as it is. Okay, this is how we find this jet characteristics. But one particular condition is that these solutions are valid when your X by R is greater than 0.375 RE. This is the minimum location where x by r can valid. And Scumming number, which is the ratio of uh, mu kinematic viscosity to the dynamic to the binary diffusion coefficient, is equal to 1. Why it is say? Because we are assuming this jet to be non-reacting, otherwise this won't be 1, because we will have a binary diffusion has a fixed value and a certain value when we are introducing the diffusion coefficients. So whatever analytically we say, this can be represented in a graphical manner, just to take care about the study what is the Reynolds number effect. So if you are increasing the Reynolds number, we see that the dimensional center line velocity increases, and at a given Reynolds number, if you are increasing axial distance, the central line velocity drops. So that means there is a velocity decay. A similar trend is also true for fuel mass fraction decay. Another important parameter which is of quite interesting is to find the jet spreading rate. So jet spreading rate is a concept we are looking at, that we define a parameter which is the jet spreading rate and spreading angle. To do that, we have to first find out jet half width. So jet half width is defined as the radial location at which jet velocity has decayed to half of its central line velocity. So we find a parameter r half by x. So when you say this decay, correspondingly we can find a spreading angle. So what we are looking at is that when the decay at any x, when you are looking at, if the jet has the ratio of the radial location at which jet velocity has decayed to half of its velocity. So radial location is in this manner and it decays to half of the velocity, and that distance is x. So that is the location what we call as jet spreading rate, which is r half by x. This is one part, and when you say by solving that equation, this turns out to be this number. It is 2.97 times r e to the power minus 1. Now when you define this jet spreading rate, then we can find out jet spreading angle. So this angle r half to this x is known as the alpha, what is called as jet spreading angle. That is tan inverse r half by x. And here this Reynolds number stands for this Reynolds number value stands with at a location which is r half, that is jet half width. So it says that this analysis says that at high Reynolds number jets are narrow, while low Reynolds number jets are wide. That is quite natural. That is initial state. During the initial phase, the jets are narrow, and when when it is spreading or at low Reynolds number, jets are wide. So through this analysis gives us some kind of generic features for a laminar diffusion flame structure. So initially it was a jet, but one can say it's not actually a jet. If it is actually a fuel air mixture, the typical trend could be like this. So instead of spreading at this, we are looking at a domain where this effect of fuel is there. So what we see here is that this is the twice r, which is the diameter of the fuel nozzle. At x is equal to 0, this fuel air mixture starts to spread, and we are looking at x. And when you talk about this very specifically, this laminar diffusion flame, for example, when you say pre-mixed laminar flame, when you create a spark, the flame is created, which is nothing but a imaginary region between the burned charges and unburned gases. That is what we visualize. Similarly, when you say laminar diffusion flame, we say that we can have a imaginary domain or shape or a trace that actually specify two regions, which is fuel rich area and which is fuel lean area. So that shape, that is called as phi is equal to 1. So that is the zone which separates two regions, which that is called as a flame zone. It separates two regions, one is rich fuel, other is the lean fuel. So below this line it's a fuel rich, above this line it is fuel lean. Again, although it is rich zone or lean zone, but one interesting thing, what happens in that axial distance. So axial distance also, this richness or lean, that value varies. If it is a rich region, that value varies. So that means initially, if you look at rich region, it is of very high strength, and as you go towards the flame zone, it becomes leaner, and at phi is equal to, stands as phi is equal to 1. Then beyond that line, we are moving towards lean regions. Similarly, if you go far away, we can have this effect, but beyond this point, this we can assume that it is the effect of fuel is not present. So we call this as a far field regions. So in this domain, it is completely air. So this is one kind of flame structures that evolves out of a jet, and we try to model them in this manner. So the flame structure which is defined, phi, which is r is equal to, or in particular we say laminar flame structure, which is phi r is equal to 0, x is equal to Lf. That means this flame length. So x is measured from here. So at this location, your x is equal to Lf. So this is how we define this flame zone or laminar diffusion flame in terms of r and in terms of x. That means that is the maximum x which can fill that flame can fill with equivalence ratio of 1. And other points I have told you already. The fluid and oxidizer is consumed within the flame, which is at reach, and the products of compositions have strong correlation with respect to equivalence ratio. Flame surface is normally defined as a contour where fuel and oxidizer meet at stoichiometric portion, which means that if you look at any point on this flame surface, the fuel air mixture is stoichiometric. This is not at a point, this is a surface. In other words, the flame surface is defined as the locus of points where equivalence ratio is unity. In some cases, we say it's a over ventilated flame where there is more than enough oxygen for the oxidizer in the surroundings to burn the fuel completely. So that means some cases when you have additionally, normally in the diesel injector, there is a direct injection, there is indirect injection. Direct injection normally comes out, but still we pump indirect injection. That is normally happens in small engines, small CI engines. Larger compression ignition engines have enough space, so that way uh, we get the flame structure of like this. But small engines, it doesn't have enough space, so we give additional fuel in a different route. So the initial flame is not not called as the flame surface. So we can say it's a over ventilated flame, but with an extra air oxidizer. So through this concept, what we can find out that because there is a quite significant variation of equivalence ratio from phi is equal to 1 lean to ridge, there are possibilities that the some says in some cases the flame becomes narrow and in some cases flame becomes wide. So narrowing the flame increases the fuel concentration gradient, that enhances diffusion, and those cases, because those cases, why it is happens, because buoyancy accelerates the flow. So the flame length, which is stands as LF, is decided by these two phenomena. Okay, that is another kind of events that we get in laminar flame structure, which is typically called as soot formation. Soot formation, uh, soot formation as well as soot destruction. So what you see is that after solving this, we get some kind of shapes. Now why this soot particle forms? Soot particle forms because we are not, it doesn't find sufficient air to combust the fuel particles, and the carbon which is there in the fuel remains as small particles. Now where is the location that soot particles can form? That can form only when we are in the within this dome, rich mixer zone. So that is the zone where, if it is, since it is an auto ignition event, not necessarily that every corner of the combustion domain the fuel air mixture will be equivalent. This is one case where this is one zone. If there are multiple fuel injectors, so there will be combined effect of all the fuel diameters. So that way we cannot precisely say that whether soot particles form or not, because it is the combined effect of pressure, temperature that decides an effective combustion zone. So let us say in a combined effect or situation, the soot particles has to form, and it normally forms where there is a fuel rich region. So the first layer of this fuel, which is called as soot particle inception zone. Now these soot particles grow in sizes. Initially it is a small droplet, and because it grows in the sizes, and they started oxidizing, because when they go to the outer core they see enough air. So it is not combusted, but it has moved to it has diffused into air. So when it starts, initially it starts with soot wings and then soot breakthrough. That phenomena is typically called as soot formation or wings, and they finally break down. So when they finally break down, we call them as a smoke. So this process talks about how the soot formation, how it then finally evolves down to smoke. So it started with the flame tip region and boils down to smoke if they are not combusted properly. So this is a quantification for this flame length LF, and which is for a diffusion flame. Simple relations. How do you find this flame LF? Through our analysis, through our laminar flame, non-laminar diffusion flame analysis, and it is a function of two important parameters: initial velocity, initial fuel flow rate, its mass fraction at stoichiometric mass fraction, and where initial fuel flow rate can be related with the initial condition with respect to its area. The next point I need to tell that how that similar concept, which is actually designed, that if you need to this particular term talks about three things. One is as if the combustion has happened, and we have fuel and air, oxidizer, and the products. So there are, for each case, fuel has its mass fraction, products will have their mass fraction, oxidizer will have mass fraction, and this is nothing but as a function of F. F is called as the mixture fraction, which is correlated to the species mass fractions with fuel, oxidizer, and products. So that definition I have given in the previous lecture. So we are looking at this F, which has a stoichiometric value, and in this zone this F value is within the less than 1, and this is the flame sheet. This F value is stoichiometric value is this side. So basically in this zone we are trying to find out the fuel and products. Here there is no fuel because we have already crossed this flame sheet zone, so we have only oxidizer and products, and on this flame sheet we have this only products. So as if on this flame sheet entire fuel air charge has combusted only in the products. So along this X we are trying to see the various value, how the temperature drops from within the flame and outside the flame. This particular curve talks about state relationship species for mass fraction, and this is for mixture temperatures. Now coming back to exact calculation of this mixture fraction, by definition we say this. So from this one can correlate this mixture fraction as a function of your fuel fraction and product fraction, mass fraction. And remember, these are the mass fractions, this is the mixture fraction. Mixture fraction talks about only the mass of material which originated from the fuel stream, MC and MH. And normally when you solve a generic version of diffusion flame analysis, we solve this kind of equations which talks about what happens inside the flame, what happens outside the flame, and what happens on the flame surface. So this is all about the diffusion flame characteristics and behavior. And just to extrapolate this in a practical viewpoint and applications, we call them heterogeneous combustions, where air fuel mixtures are not pre-mixed, and fuel sees a high temperature air, and typically this happens in CI engines, and how it evolves down, which gives the similar correlation what we have studied here for laminar diffusion flame, is like this, that normally this mechanism we have there in the CI engines, where you talk about pressure volume diagrams, pressure crank angle diagrams, and mixture is mostly heterogeneous, and defending with different normally CI engines are operated at different compression ratio, and we have fuel injectors. Their fuel is injected at a particular location of in the where at the late compression stroke. Then what happens after that? So after injection, the fuel undergoes three things: atomization, vaporization, mixing, self-ignition and combustion. So through this route, the fuel happens this. Now what we are looking at in this analysis is that what happens when it fuel vaporization and tries to mix. So in this zone, whatever study we have done, we trying to correlate. So this is how we come from a fuel injector. When the jet comes out, it is along this axial line, it is only liquid things, we try to vaporize. So in the next lecture, we will try to see that when in the liquid region, the fuel is in droplets, and that it has some initial diameter and try to evaporate. That analysis or treatment part is something different. I will come back in the next lecture. But here, what we are looking at when it comes out the jet, what is the zones that it forms. So first zone is A, which is too rich to burn. Second zone is rich and combustible. Third zone is stoichiometric. Fourth zone is D, which is lean and combustible. Lean but combustible, but E is the too lean to burn. So obviously we are moving from very rich zone to very lean zone, which is far stream. And the self-ignition occurs at zone B. So that is the most effective zone where entire fuel droplets gets combusted. And other zones are non-effective, but when they interact with when they interact with other kind of fuel molecules in which fuel is injected at different locations, they also create similar kind of combustible zone. So this is how the end results of that analysis is correlated with typical fuel injection in a engine. So rest of the things is like a textbook. I am not going to detail. So here when you talk about vaporization zone, because of its strength or equivalence ratio conditions, 90% of the fuel gets vaporized. And in the mixing zone, we have the fuel mixing takes place. This is the comfort zone of engine where we say equivalence ratio for mixing. And ultimately, when you see this particular effect, and we expect the corresponding rise in the pressure in the cylinder as a P theta diagram. Point 1 is the fuel injection, B is the fuel injection starts, B is the ignition, and up. So initial period there is a slow rise and there is a sudden rise from B to C, and at this point gives the peak pressure and peak temperature, which is adiabatic flame temperature. After that there is a decay. So this is same thing that the fuel ignition simultaneously starts in the fuel rich zone, and typically that is zone B. Then in the combustion zone, which seems to be a zone between the path B and C, and that typically this is the combustion zone period. And normally when this combustion initiates, the average piston speed in the cylinder, which is in the range of 5 to 20 meter per second. Ultimately, the C10 number of the fuel, this is another characteristics of the fuel which talks about the effectiveness of a fuel in a diesel engine applications, because the fuel has to ignite, and if it is too low, if the C10 number of the fuel is too low, then there is a greater chance of the fuel, greater amount of fuel will be injected. So this particular event, when there is a greater amount of fuel which is injected during ignition delay time, this is the time where it creates the formation of soot, and they try to spread. Then lastly, this is a concept what we call as a direct injection engine and indirect injection engine. Normally what happens, we are looking at, for diesel engines we are looking at very in the range of compression ratio between 12 to 18 to 24 or higher. But what happens is that when you look at small compression ratio, engine cylinder, although we are going for compression ignition mode, but the ignition the area does not have sufficient for us to create an environment of uh, environment which is favorable for combustion, because the fuel doesn't come as a jet for a long distance, rather it terminates at short distance, because it sees that smaller volume in the engine cylinder. So but at larger engines, at larger size engines, high compression ratio engines, normally we prefer this direct injection. Direct injection means we have, the fuel comes as a jet, it has a whatever strength it has, it can spread the way it wants. But that is not true in small engines at higher speeds. So for that reason we need to create a ambience where we can alter the jet characteristics of the fuel. So that is the reason we spray the fuel, or we create some artificial turbulence. And when you have this artificial turbulence, to have this similar effect what you need to have for a higher speed. So those are called as indirect ignition engines, which means initially there is a fuel injection, and side by side we also evolve multiple injections simultaneously. So those are called as indirect injection engines. But indirect injection engines are very prone for a uncomfortable combustion, and that's the reason diesel engines at lower compression ratio are usually avoided. So with this I conclude, and there are some review questionnaire which talks about the just to solving the problem for textbook problems, like this particular problem talks about what is the effect of Reynolds number at various values of mass fraction and fuel fractions at different R and X. So starting from the basic definitions of the expressions, one can find out Reynolds number at various locations and try to find out its the characteristics of flame, and of course we also can find out the jet spreading angle. These are some numbers which talks about how the fuel decays with respect to the expressions analyzed through the similarity solutions. So this is also similar case in which we are looking at a problem, is that in one case we are talking about exit diameter of a nozzle which is required to which is the base exit diameter, and if the what is the effect of exit diameter if you need to increase the exit velocity by 10 times. So this alters actually the Reynolds number, and as the alteration of Reynolds number, the jet characteristics changes. Similar problem we try to look for in the combustion ignition engines to find out the flame speed. This expression how the flame speed is calculated in a diffusion flame in a combustion environment. So with this I conclude. Thank you for your attention.